In this media, you will learn about ambient temperature compensation. Ambient temperature variations are generally faced in shipping environments, so individually characterized transmitters are used to compensate such variations. This reduction in variation permits the process to be done closer to the set point, which in turn results in greater output. In a filled thermometer, the total internal pressure is considered as the measured variable. The main use of the installation is to determine the process temperature around the bulb. Hence, it is necessary to remove the influence of ambient temperature variations on the reading. The error produced by ambient temperature variations is not the same for all the types of fills. The thermal system can be classified into the following classes. Class 1. Liquid-filled systems. Class 2. Vapor-filled systems. Class 2A. Liquid in the bulb is in balanced state with its own vapor. Class 2B. Only the bulb has the liquid and the rest of the system is filled with vapor. Class 2C can be operated as Class 2A or Class 2B systems. Class 2D. Two liquids are present in the bulb. One is volatile and the other is non-volatile. Class 3. Gas-filled systems. Class 5. Mercury-filled systems. If the influence of ambient temperature is compensated in both the capillary and in the readout device, the design is said to be fully compensated. Full compensated design is assigned by the letter A and is being included to the class designation number 1, 3, or 5. Class 2 systems do not require any such compensation since the liquid or vapor interface in the system is within the bulb all the time. For Class 2A filling, it is essential to retain all the portions of the capillary to have a temperature less than that at the bulb. In fully compensated 1, 3, or 5 systems, we can see that both the capillary and the spiral pressure sensor are replicated. Here, the compensating capillary is closed at the endpoint and the length of the compensating capillary is equal to the length of the active capillary without including the bulb. In order to avoid the ambient effects, both capillaries are made to run parallel to each other and both burden spirals are so connected that the ambient effects are cancelled. In mercury-filled Class 5 systems, full compensation can be offered without the expenditure of replicating most of the thermal system by using an internal wire. An INVAR wire is introduced inside the single active capillary, which is actually a nickel alloy whose coefficient of thermal expansion is very less. Hence, we can say that there is no variation in the internal pressure of the thermal system even if the ambient temperature around the capillary changes. Case compensation, Class 1B, Class 3B, or Class 5B can be attained by adding a bimetallic spring which produces a force approximately equal to the force caused by the ambient temperature variation. This is because whenever there is a change in the internal pressure with respect to the measured temperature, the volume of the burden spiral also varies. Bimetallic spring offers the case compensation that is effectually only at the bulb temperature, which is generally fixed at mid-range. As a result, undercompensation occurs at the top, whereas overcompensation occurs in the bottom half of the range. It is possible to do uncompensated operation with Class 1, liquid-filled systems when the length of the capillary is very small and with all categories of Class 2, vapor-filled systems. Class 3 and Class 5 systems must be compensated at all times. In gas-filled Class 3 systems, the capillary error increases with respect to the bulb temperature and can be minimized by raising the volume or span of the bulb. Thus, you have learned about ambient temperature compensation.